Good morning, everybody. I'm Town Peterson. I'm really happy to be here with you. This is, believe it or not, the 23rd of our global online seminar series in biodiversity informatics. So that means actually more than 2 years. That's a bit hard to believe. The bad news is you have me giving the talk again. But I hope this will be a nice change of pace. We've had ongoing a series of talks about the history of this field of biodiversity informatics. And I'm going to continue that today. So you've heard about the history of more than anything, data sharing efforts. The early part of this story was told by Arthur Chapman, the middle part by Jorge Soberon, and the most recent by John Wieczorek. Today we're going to change gears just a bit. What we're going to talk about is the history of ecological niche modeling. So this is an important technique in the field of biodiversity informatics. One technique in a toolkit of many. So I will be talking about the history of this field that has a very vibrant presence. And so I hope this will be useful in terms of putting the field in a bit of perspective. I'm going to share my screen with you right now so that we can go into this topic a bit. Now, I do want to emphasize early history, okay? And I'll come back to that in just a moment. First of all, if you have any questions, please, as the questions come to your mind, send them to this email address. And this is the email address that I can look at the end of the talk and hopefully answer your questions while the broadcast is still going. Too often we end up without questions because there's a bit of a delay in people sending them in. So if you do have questions, please send them to me as they come to your mind. Okay, so let's talk about this functionality. Essentially, it's the idea of being able to predict or anticipate the geographic distribution of a species. One of the things about this tool is that it comes under a bunch of different names. In the modern literature, the two most common are ecological niche modeling and species distribution modeling. I don't want to go into that debate right now. It's a subject for another seminar. But from my perspective, niche modeling is something that is estimating the ecological niche, which is to say the full suite of environmental dimensions within which the species can maintain populations, whereas distribution modeling might be focused on estimating the geographic distribution, which under some circumstances doesn't require a full niche model, and under all circumstances requires some assumptions about what parts of the potential distribution are accessible to the species. Again, I don't want to go into this debate in this talk. What we're really after is, why is this tool so exciting and why is this tool so popular? Well, it provides crucial information for many analyses that would be of interest in biodiversity science. For example, invasive species biology. Well, one of the big questions is, what is the geographic potential of this species? Conservation biology. If you're looking to set up reserves, you need to know where the species in those reserves are distributed. And certainly for analyses in more basic science of biogeography and macroecology, this information is crucial. And I think I personally think that this set of tools of niche modeling or distribution modeling became popular because they offer a way of getting that sort of information that is quick, it's inexpensive, it's doable. The data needed are commonly and openly available. So it's kind of a right place, right time sort of thing where this tool was sitting there for quite a while. And then when a conjunction of data and interest and activity came along, the tool took off. The use of the tool took off. So let's look at citations of either ecological niche model or species distribution model in Web of Science. And you can see one of those terms was used as early as 1983. And you can see very few citations of either of those terms until quite late, quite recently. And you can see in 2006 and 2007, and then essentially the last 10 years, you can see this massive increase. And so even in Web of Science, which is a fairly limited pool of journals because it's focused on those which are accorded journal impact factors, you can see more than 100 papers published per year in the last 2 years. So this is a tool that has become very, very popular and very, very widely used. I think we have a key point in the history of this tool, which is 2006. And you can see why it's a key point given the publication trajectory. As of 2006, use of these terms of niche model and distribution model takes off. What happened in 2006 was the publication of 2 papers. One was by Phillips and colleagues, which presented the tool Maxent, and the other was a broad comparative study by Jane Elith and colleagues, which, shall we say, presented some benchmarks about model performance. And again, that's another seminar, another topic, another debate. But the point is, those 2 papers, or at least that year, changed the history and the future of this tool. So let's in this talk then focus on this early part. Okay, all these early years, a couple of decades, where there was activity going on and people were using these tools and playing with these tools, but it was still quiet and it was still not widely accepted or widely used. And perhaps somebody else will take on the last 10 years, which are essentially the recent history. But I'll be talking to you about the ancient history. So here's an outline of what I want to talk to you about. This will be a fairly brief talk in the sense that I'm not going to go into great depth, but I just want to make mention of a bunch of things that were happening in those early years. So let's start by talking about Joseph Grinnell and essentially early activities, early landmarks in the trajectory of this idea, this tool, and this field. So there's Joseph Grinnell. Most of the time, when you're shown a picture of him, you're seeing a older man in a suit, and I'm sure that if Grinnell were alive today, this is more how he would like to be remembered. Grinnell was a consummate field biologist. In fact, he invented the field note system that has been used for about 70, 80 years in systematic vertebrate biology. You can see in this photograph, I believe he's skinning a rodent. And in fact, his collections, mostly housed at the Museum of Vertebrate Zoology, are still the epicenter of important scientific initiatives. So this is a person who focused on assembling highest quality biodiversity data, essentially primary biodiversity records that were documented by a skin of a mammal in a scientific collection, and that skin could be rechecked and reviewed, and it's essentially a permanent documentation of that record. So Grinnell, apart from his survey and inventory work, also did a lot of thinking about species geographic distributions. And so this is one of my favorite papers, published by Grinnell, I believe in 1914 or 1917, the niche relationships of the California thrasher. And essentially what you can see in the map is dots and triangles, which mean different things. Of course, I've covered up the legend, so you can't see that. And you can see an outline map that was probably drawn by Grinnell, thinking about what he knew about the distribution of those points and the distribution of habitats and ecosystems that the California thrasher likes. I'll give you a bit more of an illustration of Grinnell's thinking. He published another paper, Field Tests of Theories Concerning Distributional Control. And in this paper, he looked at a bunch of species, but he also presents a list of essentially the factors of the environment that might exert control over distributions of species. And so this is essentially the first couple of statements of the idea of ecological niche. And if we look at Grinnell's list, it's mostly about vegetation, food supply, rainfall, humidity, wetness, dryness, barometric pressure, elevation, atmospheric density, safety, availability of hiding places, availability of water, availability of land, or existence of water, existence of land as barriers, cover and shelter, nature of the substrate, insulation, cloudiness, temperature. So the great majority of factors that Grinnell considered were what we would call abiotic in nature, which is to say these are characteristics of the environment, and the species needed certain sets of conditions, certain subsets of the whole availability. And so in many parts of the literature going back decades, the Grinnellian ecological niche has been discussed as essentially in terms of abiotic requirements of the species. Now, of course, nothing is perfectly clean in this world, and so notice the last few of these on this list: interspecific pressure, competition, parasitism, and individual preferences. So at least the competition and parasitism are interactions amongst species. And in that sense, Grinnell added in some aspects of the niche that were not abiotic. But we're going to focus on the gist or the bulk of his commentary, which was mostly about niche as requirements. And if you'd like to see more discussion of this point, Chapter 2 and Chapter 3 in a book that 6 colleagues and I wrote in 2011, Ecological Niches and Geographic Distributions. Those 2 chapters present quite a bit more detailed discussion of this point. So more than anything, what I'd like to do is illustrate Grinnell's thinking by giving you just a bit of part of one of his I'll call them niche models. He's talking about the Oregon jay, which is a small corvid that's in high elevation forests in the western US and Canada. And here, let's listen to what Grinnell has to say. In the interior of California, it does not descend below a certain altitude. Now, three other factors in its distribution are quite obviously connected with that of altitude, namely barometric pressure, atmospheric density, and temperature. But when we take into account the fact that the Oregon jay exists at or close to sea level around Humboldt Bay, the first two factors, those of pressure and air density, are instantly eliminated because of the obvious fact that the bird successfully maintains itself in localities of widely differing altitude. So what are we seeing here? But in the early 20th century, we're seeing Grinnell taking those occurrence points, essentially primary biodiversity data records, and he's discussing each one in terms of the independent variation of these factors that he was interested in. He sees a correlation, which is that this is a high elevation species. He comes up with three reasons why those elevations might be meaningful to this species, and then he comes up with other occurrence points that invalidate two of them. So really, this is a pre-GIS correlational ecological niche model. And Grinnell presents in a variety of papers, perhaps 10 or 12 of these verbal niche models, and then turns them into maps of species distribution. So really, if we don't penalize Grinnell with the fact that GIS and in fact computation hadn't yet been invented, then he really was doing pretty much what we're doing right now in terms of ecological niche modeling. Now, this word niche perhaps was too useful for its own good. And so by 1927, in a book called Animal Ecology, Sir Charles Elton writes a very different meaning of the word niche. Remember, the Grinnellian version of niche was the requirements of the species in terms of environment. And Elton instead says the niche of an animal means its place in the biotic environment, its relations to food and enemies. And so this is a very useful concept, but it mixes in the idea of role or interactions into the idea from Grinnell of requirements. I have no problem with the concept. I have a problem with the idea of recycling the same word and giving it multiple and very different meanings. G. Evelyn Hutchinson, 2-3 decades after Elton's book, Hutchinson cleaned up these ideas a bit, but still had this mixture of niche as requirement with niche as role. And this is really something that we're dealing with to this day in the literature, because one person says niche and another person may not understand exactly what that person was trying to refer to. Now, at the same time as there are early confusions, there's also early points of light. This is a favorite of mine. This is about early efforts by the US Fish and Wildlife Service, shall we say, to improve North America for hunters. So I'm just going to read a bit of this to you. The program of the US Fish and Wildlife Service to import desirable game birds and mammals has shown the potential of such importations to the outdoor recreational resources of the nation. The program should be encouraged. I'm skipping. Bureau of Sports Fisheries and Wildlife should be urged to step up its program to trap and otherwise acquire game birds whose value has been determined by the surveys already accomplished. And you can see down at the bottom, this resolution commends the Bureau of Sport Fisheries and particularly Dr. and Mrs. Gardner Bump for the outstanding work that has been done to date on a limited budget. So essentially what Fish and Wildlife Service was doing was targeting particular game bird species, going to the country of origin of those species, trapping those birds and bringing them back. So here's a newspaper article from Georgia from 1952. And again, Dr. Bump is being congratulated, but the commentary is, we haven't found anything to add to the quail, dove, and wild turkeys, which are the native game birds in Georgia. Wish we could. Georgia's hopes to establish pheasant has been a great big bust. The chukar efforts also fell apart. The chukar we released just simply vanished. We don't even know what happened to them. Some ornithologists have come out against efforts to introduce exotic game birds in this country. Blah, blah, blah. There's room for argument on both sides. So I think a lot of us biologists now would come out against efforts to introduce exotic anything into any country. But this is a 60-year window into history about how different these attitudes were in the 1950s. Well, Gardner Bump was working for Bureau of Sport Fisheries and such, and was very much focused on these introductions. And so here's a report that was published, Red Junglefowl and Kalige pheasants. You can see it's published by the Fish and Wildlife Service. And there's some very interesting things that Bump does in this, and this is one of the most exciting. Notice figure 5, areas in the southern United States with climate rather similar to red junglefowl range in India. And he classifies the southeastern US into 3 zones. The southernmost, the southeasternmost, is labeled as excellent possibilities like range in India. And then the middle zone, fair to good possibilities, winters slightly cold, and then borderline winters perhaps too cold. So to my eye, once again, what we're seeing is an ecological niche model. And this is a niche model because it required essentially a view of the species' full environmental potential as it was manifested on the native range of the species. So this is an exercise that we are doing today. Different tools, more data, but what did Gardner Bump do but to create some mental or textual or perhaps quantitative model of the temperature range under which red junglefowl were distributed in the species' native range, and then he transferred that model to North America and used that as a guide for where the species might be introduced successfully in the US. And just as a historical side note, the species was introduced into the US in the regions that Bump had chosen as most adequate. And curiously, the individuals apparently survived quite well, but as soon as the females sat on eggs to reproduce, apparently mortality was essentially absolute. So maybe that is a biotic effect creeping into the niche as requirements. Okay, so that's a quick and spotty view of essentially the first half century of the idea of niche and niche models. Essentially, Grinnell threw out a very exciting term, which was immediately grabbed up for a bunch of related ideas. He also threw out some very interesting ideas about distributional ecology. And we can see those being used even in very serious applications. But really, organized initiatives don't begin until perhaps the 1970s. I want to point out 2 national initiatives and 2 analysis initiatives, and just give you quick illustrations of these activities. These are very early, so you may be shocked to see what these people were doing, what they were dealing with as far as data management. So first, let's go to a great point of light. The Environmental Resources Information Network of Australia. Here's an announcement of the launch of ERIN. Essentially, the Minister for the Arts, Sport, the Environment, and Territories spoke at a ceremony officially launching ERIN, and the statement was made: a national information system allowing ready access to key information on the Australian environment is a major government initiative to support and advance requirements for ecologically sustainable development. So wouldn't we love to see that announcement in many countries around the world today, 40-some years later? And of course, ERIN had already gotten quite a bit of activity. And so there's the comment, ERIN essentially already uses the latest geographic information systems technology. It has developed many thematic databases, coordinated data standards, and initiated successful collaborative projects. So this is the beginning of a very important catalyst in the world of biodiversity informatics. And you can listen to Arthur Chapman's talk, which gave quite a bit more detail on ERIN. One thing that I noticed as I was going through early ERIN documents was the focus on data quality. So even in this extremely early stage where quite a bit of effort was needed just to have access to any data, I'd like you to notice that there's a lot of focus on data quality. What, the buzz phrase today is fitness for use. They talk about data quality as an essential or distinguishing characteristic necessary for spatial data to be fit for use. Accuracy, the closeness of results of observations or estimates to true values. What is error? And so ERIN has instituted several procedures for handling data errors, data quality, and data accuracy. And this is a lesson that really needs to be heard now, because many of the biggest biodiversity data portals have been criticized because, yes, there are lots of data, and yet the data quality is not as high and not as good, such that we can use those data without worrying about whether the quality turns into bias and error. So these are lessons from history. ERIN had nowhere near as much data as it has now in the form of the Atlas of Living Australia, but quite a bit of data. And so here you can see a map of endangered and vulnerable plant records and rare plant records, but also you can see big gaps in the information. that were used to guide subsequent efforts. And you can also see some information products where we start to see integration across many species. And so this is a map of landbird species richness that was produced by Aaron. And you can see that the species poor sites across the country have under 50 species, and the species rich sites across the country have as many as 240 species. Aaron's activities and early activities across Australia led to quite a bit of exciting activity in terms of developing, shall we say, niche modeling algorithms. So here's a paper published just a couple years ago about Biochem, and the title is the First Species Distribution Modeling Package, Its Early Applications and Relevance to Most Current Maxent Studies. We'll come back to Maxent. But the authors, who are four important figures in this early Australian period, the authors state the earliest SDM studies are dealt with only briefly, even in these books and reviews published recently. I am a co-author of one or more of those books, so I guess I'm guilty. Consequently, although we did mention Biochem clearly, consequently, many researchers are unaware of when the first SDM software package, Biochem, was developed, and how a broad range of applications using that package was explored within the first 8 years following its release. So this paper essentially lays out those early advances, and again, most of these either were in Australia or were stimulated by work in Australia. In that same paper, we see comments, introduce interest in species distribution models and related niche studies has increased dramatically in recent years. Skipping to the second one, important conceptual elements underpinning the development of Biochem can be traced back to Evelyn Hutchinson's formalization of the niche concept as a series of independent environmental variables. I would say, well, what about Joseph Grinnell, who formalized the niche concept as a set of requirements on the part of each species? Anyhow, nobody's denying the importance of Hutchinson's contributions, but let's not forget about deeper history when we're reminding people of history. So let's look at some of these early Biochem studies. Here's an analysis, comparative responses to temperature of the major canopy species of Tasmanian cool temperate rainforest and their ecological significance. And this is a paper on net photosynthesis, which was based on actual measurements, and climate analysis, which was based on use of the Biochem algorithm. And for those of you who very conveniently turn on your GIS system and bring up beautiful maps, I'd like you to notice this early raster display where minus signs, equals signs, plus signs, and black dots are used essentially to give a graded series of suitability. So those of you who grew up with ArcGIS and QGIS, there but for the grace of God you go, eh? GIS technology in this period was quite a barrier, quite an impediment, because it required quite a lot of work just to do basic display functions. So in Mexico, more or less in parallel, there was also quite a bit of activity happening in the late 1970s and early 1980s. A lot of this activity can be attributed to this man, Arturo Gomez Pompa, but also Lauren Giddings and Margarita Soto, several people, mostly botanists, started exploring not just niche modeling, but also more broadly biodiversity information management. Another thing that I'll give you a bit of a reminder of is how hard data management was. This, you can see this card here, is a data record. And essentially, you can see 1, 2, 3, 4, 5, 6, 7, out to 80. And then you can see these punches, right, where different little windows are removed. And so depending on what you wanted to enter, you were able to enter data of up to 80 characters. And those data were recorded as a set of punches in this card. And so you can see this data record says Biblioteca Instituto de Geología UNAM, so the Institute of Geology Library at the National University of Mexico. You can see a literature citation. Essentially, this is just trying to create a basic bibliographic record, and it took, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9 of these cards. Imagine the rich data records that we manage now and how complicated that would have been to keep in paper format and in a format that had to be then read mechanically. So these early botanical efforts in Mexico focused quite a bit on assembling sets of data, just as had happened in Australia, which I didn't mention. Here's a list of the data sets that they assembled. The outline of Veracruz. Veracruz is a state in eastern Mexico where a lot of this activity was focused. Maximum rainfall in 24 hours, annual rainfall, hot zones, imperceptible precipitation, temperature contours, temperature variation, climates, elevation, vegetation, stormy days, types of soil, etc. So this really does sound quite a bit like the list of factors that limit species distributions that Grinnell provided to us. So really, this is very much in that line of thinking. Here's another early map. This is a map of the distribution of a plant called Oreopanax. And again, notice that it's done using a dot matrix printer and making creative use of symbols. And then here is essentially a photograph of a screen of a computer showing an early range map. So again, give thanks every time you turn on your nice modern GIS system. So those are two national initiatives. And in fact, those two countries have exchanged back and forth for many years now. If you listen to Jorge Soberon's discussions of the middle history of data sharing, he talked about an early visit by Mexican biodiversity scientists to Australia to essentially pick their brains and get the benefit of that early exciting activity. Now, another early activity in Australia was that of Climax, and Climax is an analysis system that is used still today. Here you can see version 3 of its user's guide. And essentially, and I'm not the best person in the world to explain Climax, but essentially Climax is built around this, this idea of a niche being requirements with respect to abiotic conditions across landscapes. And it's built around the idea of optima near the middle of the niche, and then increasing stress near the edges of the niche. Darren Kritikos was kind enough to supply me with some of these visuals, but within Climax, the species ecological niche is defined in terms of response to environment, and the environments in which the species can persist. To my eye, Climax is an interesting mixture of correlational niche modeling and process-based or first principles niche modeling. In Climax applications, population and growth are assessed weekly and then integrated across the full year. And so to persist at a site, the species needs to grow sufficiently during the good parts of the year to make up for population losses during the bad parts of the year. And the overall potential for persistence is summarized as what they call an ecoclimatic index. And so different sorts of stress might affect a species in different parts of its distribution. Here's a diagram for North America. It looks kind of centered on Kansas, where I live, but you can see towards the south, increasing heat stress, and towards the north, increasing cold stress, and towards the southwest, dry stress, and towards the southeast, wet stress. And the idea of Climax is to take these different stresses into account. And as I said earlier, the good part of the year, the growth season, has to offset or more than offset the bad parts of the year, which here is called the survival season. And you can see Climax outputs in terms of this sort of map. Here's a map for the codling moth in Europe and Asia and Africa. Essentially, the blue dots are places that are firmly within the estimated niche, and the X's are places that are firmly outside. And here's a global view for the same species. And so to a niche modeling eye, this is a map of the potential distribution of a species. This is a map of A in the band diagram, and obviously a species with this sort of distribution might in reality be endemic to only Europe or only New Zealand, or it might have a near global distribution and be in all of these places that you see in blue. Now, another line of work that goes back quite a ways is this idea of gap analysis. Here's an early publication, Gap Analysis, a Geographic Approach to Protection of Biological Diversity. And so the biggest view of gap analysis was to map land cover of dominant ecological systems, to map and model the ranges and distributions of the species within those ecological systems, to map land tenancy and land stewardship and protection, and essentially to detect gaps in the coverage of the species and the ecosystems by the protected areas or by the land tenure system. This was a US government-funded initiative during many years. Perhaps, well, I won't say perhaps. The methodology is certainly something that would not be seen terribly positively right now. Just to give you an overview, essentially there was a synthesis stage of assembling information and essentially establishing that a species is present in a particular geographic unit. So the maps here are shown for the US state of Idaho. But then information is harvested from sources such as wildlife habitat relationships, documents, databases, species-specific accounts of habitat preferences. And so that is turned into predicted presence in a vegetation cover type. And so once you know that sage grouse exists in Idaho and that sage grouse likes a particular vegetation type, you overlay those two things in a GIS, and you may apply further physical or ecological filters, like only above a certain elevation. And then you have, as a result, the predicted distribution within a polygon. And I'd point out that this thinking framework doesn't really obtain any information directly from primary data, but rather is looking for secondary information that has been synthesized. This species likes pine forest, or this species is only above 2,000 meters. So again, this is a dated methodology, but it was certainly a dominant and important methodology in the North American milieu. And again, you get these maps of species richness that were developed using the GAP methodology. So I'm not purporting to give you a full summary of everything that was going on, but that's an idea of those earliest years. Essentially, what was going on before the conceptual framework of niche modeling was in hand, but where a lot of those earliest ideas were being translated into products that I think today should and would be called niche models. Now, we can go into kind of a second phase where we start to see the appearance of complex algorithms. And so Biochem, that earliest methodology, was based on non-interacting intersections of multiple environmental dimensions. So if we have temperature from 10 to 20 degrees and rainfall from 1,000 to 1,200 millimeters, then the niche model was simply the intersection of those two ranges. So earliest were a set of efforts to essentially refine those response shapes. So focus on panel A up here. The Biochem model, if we have two environmental factors, E1 and E2, the Biochem model was essentially the intersection of the range with respect to E1 with the range with respect to E2. But we saw some early efforts to essentially cut out these corners that probably are ignoring known correlations between variables. And so these efforts like Habitat, published by Walker and Cox in 1991, that was an early effort to essentially trim down to a more relevant subset of the Biochem box. And in panel B, you can see a model using this algorithm called domain, which actually saw quite a bit more use until relatively recently. And this was essentially, rather than fitting an envelope around the points, this was fitting envelopes around individual points. Now, a big step forward in complexity, but also relatively early, developed in the late 1980s, I believe, was this idea of GARP. GARP has had a couple different names, both published by its creator, David Stockwell, but genetic algorithm for rule set prediction or rule set production. I certainly benefited from the existence of GARP for many years. I used this algorithm quite a bit. Genetic algorithms are the idea of essentially mimicking chromosomal evolution in computation. And so the idea was to seed some initial rules, something like a biochem model between this and this elevation and between this and this level of rainfall, and then to tweak or perturb those rules via an evolutionary process and allow, get this, the data to guide the evolution of a more complex model. And then along a perhaps different line of evolution of these approaches, we also see application of more and more complex and sophisticated multivariate statistical approaches. And certainly the early light in this area is Mike Austin, but this area of work has seen considerable subsequent development. Just to name a few names, Wilfried Thuiller, Jane Elith, several other people have added massively to essentially this idea of statistical analysis of species responses to environmental gradients. Here's an early paper by Austin. He took advantage of a vegetation sampling program with 6,080 plots across an environmental space, and you can see a temperature rainfall plot here. The numbers in this grid are the numbers of samples taken of each of these environmental combinations. So this is an amazing data set. And here are the response curves that Austin fit to those data. And considerable subsequent development has taken this sort of response curve and gone back to mapping to identify potential distributions of species. So very much a niche modeling endeavor. So again, that is picking and choosing and presenting a very spotty view of what we could call a middle period of development of ecological niche modeling. But then I think we can just mention briefly what I would call the end of the beginning, and that's this year 2006. First thing that happens is the publication of this paper, led by Jane Elith and Catherine Graham, and co-authored by a whole bunch of people, myself included. The title is Novel Methods Improve Prediction of Species Distributions from Occurrence Data. And the way this project was set up was, it was set up to assess how well can distributions of species be anticipated from, the way we put it back then was museum-style, presence-only occurrence data. So Austin's work benefited from having those beautiful abundance data, that's not presence only, and also from knowing absences of species. And so the Elith et al. Paper was centered on the idea of, what if you don't know anything more than presence or absence, and what if you don't have concrete data documenting absence? And so this paper was I think, important in that sense. And you can see it's been cited more than 4,000 times in the 10 years since it was published. Another important early paper, late paper or end of beginning paper, was this one. And actually there were a few early publications of the maximum entropy algorithm. Here's one by Stephen Phillips and Anderson and Shapir, published in Ecological Modeling. I wanted to include views of this paper, but of course it was published in an Elsevier journal, so it would have cost me $36. So instead, I'm just showing you the view, and you don't get to see views within the paper. But I just want you to see the amount of citation. This paper has been published, has been cited 5,400 times. Another early Maxent paper has been cited another 1,000 times. So these are massively important papers. Maxent has been a superbly useful and flexible algorithm that has become enormously popular. We could even see it as the star of this field of niche modeling. Many perhaps would argue that use of multiple algorithms would be a better idea. But again, that's the subject for a different seminar. The important point is, if we go back to that histogram that I showed at the beginning of the talk, the important point is between the Elith et al. Paper, essentially demonstrating the utility of the method, and the Maxent papers offering a very easy to use and very flexible algorithm for doing this sort of work, 2006 becomes a key year and essentially puts an end to the beginning of the early history of ecological niche modeling and species distribution modeling. And yes, I've been talking for almost an hour, so I'm going to sum up now. Let's think about what was achieved in those early years. Well, certainly one important step was the idea of talking about niche rather than distribution. That was an important difference in thinking, because if we think, as I certainly did when I started into this field, if we think about predicting distributions, then models that are calibrated only in environmental dimensions will invariably overpredict distributional potential, because they're predicting they're identifying the potential distribution, not the actual distribution. These are models of suitability and not presence. That's much the same point, but it's the idea that there are lots of reasons why a species may not be present in a place that is environmentally suitable. There was the beginnings of the realization of the importance of across what area do we calibrate these models. And certainly by the end of the beginning, essentially with the Elith et al. Paper, there was the point of the importance of simple models versus complex models to estimate these niches. And I think this is a topic that we're perhaps going to come back to. The Elith et al. Paper argued that complex response surfaces were better. And I think that's an idea that we will be revisiting in coming years, and perhaps even changing our point of view on. What are the lessons that remain to be learned? Well, I think there's a lot of work left to do in the area of model evaluation, which is to say, when you evaluate models, what does that mean as far as what is a good model and what is a bad model, and what does it mean to make a good prediction or a bad prediction? I think there's an important concept which I irreverently refer to as garbage in, garbage out. If we don't go back to those early Aaron lessons about data quality, then we may put garbage into our modeling algorithms and get garbage out of our modeling algorithms. And I would argue that another coming lesson is that individual algorithms are perhaps less important. You can see my biases coming in here. Essentially, it may well be that there is no perfect algorithm, and so perfecting an algorithm doesn't get us very far. And it may be much more important to get the ecological framework and the biogeographic framework right to be able to let any one of these algorithms that we have available to us perform optimally. And so I would argue that those frameworks, they certainly need to be improved and made more comprehensive, but I would argue that they are a crucial basis for building models. So that's a Town Peterson view of the early history of ecological niche modeling. I hope I have not said anything to offend or ignore anybody. If I have, it certainly wasn't intentional. Rather, I'm trying to paint a picture, as Booth and colleagues pointed out in 2014, trying to paint a picture of the roots of this field and the roots of this tool that have become so popular and so widely used. And so that's my real objective in all of this. Before I close, I will point out we have a next chapter in our history series. Donald Hoburn, the executive secretary of the Global Biodiversity Informatics Facility, has agreed to give the May seminar. So this will be the last Thursday in May. And the seminar will be about the history of GBIF. GBIF is the largest data aggregator in existence, 640 plus million records online and available to you right now. So this is a massive effort, and Donald has graciously assented to give a seminar on this topic. So with that, please, again, send me questions. I'm going to stop sharing the screen so that you can, there you can see a view into infinity. Stopping sharing the screen. This is me. I'm sorry about that. Might be a shock. Let me just see if we have any questions that have come in. Please do send your questions. If you don't, I'll have to answer later by email. And I will point out to you that the seminar series is very, very much open to suggestions. So please, if you have suggestions of topics or of new capabilities, new functionalities, something you'd like to hear about, please let me know. Put it in an email to the email address that I just showed you, and recommend topics, and I'll do my best to get them addressed in future seminars. Mateus Ribeiro from the Universidade Federal de Goiás in Brazil has sent in a question. Hi, Town. You explained about the initial concepts of niche, Grinnell and Elton, but I'd like to know what you think about the terms by Whitaker, niche, habitat, and ecotope. Could these terms be terminological noise? Thanks, Mateus. Very good question. I tried my best to keep this on the simple side to paint a clear picture. But yeah, Whitaker puts out some very useful terms. Hutchinson put out some very cumbersome but useful terms. The senopoetic and bionomic aspects of niches. There's a lot of terminology. There's a lot of a lot of use and perhaps even uncareful use of homonyms and synonyms in the literature in the 20th century. So I'm not criticizing anybody, and I'm not ignoring anybody. I'm just trying to distill down to concepts that are useful now. The way my colleagues and I have distilled it down even abandons the idea of abiotic versus biotic niches, and instead focuses on interactive dimensions of the niche, which is to say aspects of the environment of an organism that do not respond to the population or to the presence of that organism, versus other aspects that respond and interact with the organism. So for example, the temperature at a place really does not respond to how many small rodents are present in that place. But the amount of seed resources available as food very definitely does depend on the population of that small mammal. So yeah, terminological noise, there's been a century of terminological noise, and it goes on today. If you look in the literature for uses of the word niche, you will see that maybe only one in five papers that mentions the idea of niche ever tells you which niche, the fundamental, the existing, the realized. And to me, those are absolutely crucial distinctions. So yeah, terminological noise, perhaps we've all been guilty of it, but it's there, and so I've tried in this talk, I've tried my best to simplify things down to an essence. I don't see any other questions coming in, so I'm going to end this this hangout. I hope this has been useful to people. And again, please send suggestions to me. My personal email is town@ku.edu. Send suggestions to me, and I'll do my best to incorporate those topics into future aspects of or future seminars on the Global Online Seminar Series. So thank you very much for your patience for these 67 minutes. And this video will be online archived on the Biodiversity Informatics Training Curriculum webpage and YouTube channel in case you want to share it. So thanks again, and very best to everybody. See you next month, last Thursday of the month, when we have Donald Hoborn talking about the history of GBIF. All the best. Bye-bye.